Imagine looking up at the night sky, stars twinkling like distant memories against the velvet darkness. The cosmic tapestry stretches before us, vast and mysterious, each point of light a sun perhaps surrounded by worlds we may never know. But what if our universe, with all its galaxies and wonders, is not alone? What if beyond our reality lie countless others, parallel universes dancing in a cosmic ballet we cannot see? Welcome to a journey of wonder and possibility. As you relax and listen, allow your mind to wander through the corridors of existence itself, beyond the familiar boundaries of what we call reality. The question before us is both simple and profound, innocent yet revolutionary. Do parallel universes exist? And if they do, could they somehow communicate with each other? Scientists have long wondered about the nature of reality. Is what we see and experience all there is? Or might there be more, hidden just beyond our perception? The idea of parallel universes has captivated human imagination for generations, appearing in our stories, our dreams, and increasingly in our scientific theories. From quantum physics to cosmology, from mathematics to philosophy, the concept of multiple universes has gradually moved from science fiction into the realm of serious scientific inquiry. Tonight, as you drift towards sleep, we will explore these cosmic questions together. We will venture into realms where physics meets philosophy, where mathematics touches the mystical, where the boundaries of knowledge blur into the unknown. Our journey will take us through quantum landscapes and higher dimensions, through theoretical frameworks that attempt to describe what might exist beyond the horizon of our observable universe. The multiverse. The word itself conjures images of infinite possibility. It suggests not just one universe, but many, perhaps infinite universes existing alongside our own. Each might be similar to ours, or wildly different, with unique laws of physics, alternate histories, different versions of you making different choices at every crossroads of life. Perhaps somewhere, another you is listening to these very words, wondering about your existence as you wonder about theirs. Our journey will be one of gentle contemplation. We need not rush to conclusions or certainties. Instead, let us approach these profound mysteries with openness and curiosity, allowing the questions themselves to guide us through cosmic landscapes both strange and beautiful. Let the concepts wash over you like cosmic waves, soothing yet stimulating, calming yet inspiring. As we begin, take a deep breath. Feel yourself becoming part of this vast cosmic story. The air in your lungs contains atoms forged in ancient stars, connecting you to the universe in ways both intimate and profound. Your consciousness, whatever its ultimate nature, allows you to ponder these great mysteries, to reach beyond the immediate and touch something greater than yourself. The night is long, the universe is wide, and we have all the time we need to wander among the stars and ponder the whispers that might travel between worlds. What secrets might the cosmos be sharing, if only we knew how to listen? What messages might be crossing the boundaries between universes even now, encoded in ways we have yet to understand? Scientists speak of quantum entanglement, of particles that remain connected across vast distances, sharing information instantaneously in ways that seem to trouble even Einstein. Could such connections exist not just within our universe, but between universes? Might the fabric of reality be more porous, more interconnected than we ever imagined? Some theorists propose that our universe might be just one bubble in a cosmic foam of universes, each born from quantum fluctuations in a greater space we cannot directly observe. Others suggest that every time a quantum event occurs with multiple possible outcomes, reality branches, creating new universes where each possibility plays out. Still others speak of brains, vast cosmic membranes floating in higher dimensional space, occasionally colliding to create new universes in cataclysmic events like our own Big Bang. As we explore these ideas, remember that we stand at the frontier of human knowledge. The questions we ask may not have definitive answers yet, perhaps not in our lifetime. But there is value in the asking, in the contemplation, in allowing our minds to expand beyond the everyday and touch the cosmic. So relax, breathe slowly, and join me on this journey through the multiverse. Let the wonders of cosmic possibility carry you gently towards sleep, toward dreams that might, in their own way, be glimpses into parallel realities we can barely comprehend. For tonight, we are cosmic explorers, venturing into the greatest mystery of all, the true nature of reality itself. To understand if universes can communicate with each other, we must first explore what parallel universes might actually be. The concept may seem like science fiction, but many serious physicists and cosmologists have developed theories suggesting that our universe might be just one among many. Let us gently walk through these fascinating possibilities. The term multiverse refers to the hypothetical set of multiple universes that together comprise everything that exists. Our universe, with its hundreds of billions of galaxies, might be just one bubble in an infinite cosmic sea. These other universes might exist right alongside ours, perhaps separated by dimensions we cannot perceive, or they might be vastly distant from us in ways we cannot easily imagine. Max Tegmark, a physicist at the Massachusetts Institute of Technology, has proposed a useful classification system for different types of parallel universes. He organizes them into 4 levels, each more expansive and abstract than the last. Level 1 describes the simplest type of multiverse. It suggests that space extends infinitely beyond what we can observe from Earth. Our observable universe is limited by light that has had time to reach us since the Big Bang, approximately 13.8 billion years ago. This creates a cosmic horizon, similar to the horizon we see on Earth. Just as lands exist beyond Earth's horizon that we cannot see, so too might there be regions of space beyond our cosmic horizon. In a level 1 multiverse, these distant regions would follow the same physical laws as our own universe. They would have formed from the same Big Bang, but because quantum events and random processes would play out differently in these regions, they would develop into different configurations. Given enough distance and enough time, eventually, all possible arrangements of matter would occur. This means that somewhere, unimaginably far away, there could be exact copies of our Earth, our solar system, even copies of you and me, making slightly different choices in their lives. Imagine rainfall on a vast plain. Each raindrop creates its own expanding circle of ripples. Our observable universe might be just one such circle, with others beyond our view. These other regions would be as real as our own, but forever beyond our ability to contact or observe directly because of the limitations of light speed and the ongoing expansion of space. Level 2. In Tegmark's classification takes us deeper into theoretical territory. This level describes bubble universes, regions that form within a larger expanding space. According to inflationary cosmology, the very early universe experienced an incredibly rapid expansion called inflation. While inflation ended in our region of space, allowing stars and galaxies to form, it might continue eternally in other regions, creating a vast sea of bubble universes, each with its own Big Bang moment. These bubble universes might have different physical constants and even different physical laws. In some, the strength of gravity might be stronger or weaker. In others, the electromagnetic force might behave differently. Some bubbles might collapse almost instantly, while others might expand forever. Our universe would be just one bubble among countless others, each with its own unique characteristics. Picture a cosmic champagne glass filled with bubbles rising to the surface. Each bubble is its own universe, with its own space and time, expanding and evolving according to its internal rules. Some bubbles might occasionally touch or even merge, but most remain forever separate. Islands in an ever-expanding cosmic sea. In this framework, our universe is finely tuned for life. If the fundamental constants were even slightly different, atoms might never form, or stars might never shine. Some scientists suggest that this fine-tuning becomes less mysterious if there are billions upon billions of bubble universes with different properties. In that case, we naturally find ourselves in one of the rare bubbles where life is possible, because we could not exist in the others to observe them. Level 3 takes us into the realm of quantum mechanics and the many worlds interpretation. Quantum physics tells us that particles can exist in multiple states simultaneously, a strange property called superposition. When we measure a particle, we find it in just one of those states. The many worlds interpretation suggests that all possible outcomes actually occur, but in different branching realities. According to this interpretation, every quantum event where multiple outcomes are possible causes reality to branch into parallel universes, each containing one of the possible outcomes. Since quantum events happen constantly and everywhere, this would create an almost infinite branching tree of parallel universes, all slightly different from each other. Imagine a tree with countless branches, each branch representing a different timeline, a different version of reality. Some branches remain very similar to our own, differing only in the position of a few particles. Others diverge dramatically, perhaps containing versions of Earth where dinosaurs never went extinct, or where human history took entirely different turns. In these parallel worlds, versions of you might exist who made different choices at key moments in life. Perhaps you chose a different career, married a different person, or lived in a different city. Each decision point would create new branches, new parallel selves living out different possibilities. This interpretation suggests that the universe we experience is just one branch of an ever-growing tree of possibilities, each equally real. Our sense of a single definite reality would be an illusion created by our inability to perceive these other branches. We only ever experience one path through the quantum maze, but all other paths would continue to exist and evolve in parallel. Level 4, the final level in Tegmark's classification, is the most abstract and encompasses all possible mathematical structures. This level suggests that any mathematically consistent set of physical laws might exist as a universe somewhere in the multiverse. Our universe would be defined by its particular mathematical structure, but other structures would define other universes, some so alien we can barely imagine them. Some of these mathematical universes might contain 2 time dimensions or 10 spatial dimensions. Others might lack time altogether. Some might operate according to completely different logic than our own. The only requirement would be mathematical consistency, the absence of logical contradictions within their structure. Alongside these 4 levels of multiverse theory, there are other frameworks that physicists have proposed. String theory, for instance, suggests that our universe exists on a 3-dimensional membrane, or brane, floating within a higher dimensional space. Other branes might exist parallel to our own, occasionally interacting through gravity or other forces. Brane theory envisions our universe as a slice within a higher dimensional reality, like a sheet of paper in a stack. We can move freely within our sheet, our familiar 3 dimensions of space, but we cannot easily perceive or interact with the other sheets. Yet these other branes would be just as real as our own, perhaps with their own stars, galaxies, and forms of life. Another intriguing possibility comes from holographic theory, which suggests that our 3-dimensional reality might be encoded on a 2-dimensional boundary, much like a hologram. If this is true, our universe might be one of many holographic projections from different boundaries, each containing its own complete 3-dimensional reality. The concept of parallel universes also appears in cyclical models of cosmology. These propose that our universe goes through endless cycles of big bangs, followed by big crunches or other forms of reset. Each cycle would create a new universe with slightly different properties. In this view, parallel universes would exist not in space, but in time, one after another in an eternal sequence of cosmic rebirths. While these ideas might sound speculative, many emerge naturally from our best physical theories when we follow them to their logical conclusions. String theory, inflation, and quantum mechanics all hint at the possibility of realities beyond our own. The mathematics that successfully describes our universe often suggests the existence of others. Of course, we must approach these ideas with scientific caution. A theory may be mathematically beautiful, without necessarily being true. The challenge for physicists is finding ways to test these ideas against observable reality. How can we detect the influence of other universes if they exist? What evidence might they leave in our cosmic neighborhood? As you contemplate these possibilities, imagine yourself standing on a beach at night, watching waves roll in from an unseen horizon. Each wave represents a universe, rising and falling in the cosmic ocean. Some waves might occasionally intersect, sending droplets between them, brief moments of connection in the vastness. Could our universe be exchanging such droplets with others even now? Could signals be passing between parallel realities in ways we have yet to discover? The question of parallel universes leads naturally to our next inquiry. If such universes exist, could they somehow interact? Could information pass between them? Could we ever detect their presence or communicate across the boundaries that separate us? As we continue our journey through the multiverse, remember that we walk the fine line between established science and theoretical possibility. What seems impossible today might become tomorrow's scientific consensus. The history of physics is filled with revolutionary ideas that initially seemed too strange to be true. Perhaps parallel universes will someday join that list of strange ideas, confirmed by observation and experiment. For now, let these concepts float gently in your mind. Allow yourself to imagine the cosmic possibilities without needing absolute certainty. The multiverse invites us to expand our conception of reality, to consider that existence might be far grander and more diverse than we ever imagined. And in that expansion lies a profound kind of wonder, a cosmic perspective that reminds us how remarkable it is that we exist at all, here in this particular universe, contemplating all that might lie beyond. Among all theories of parallel universes, perhaps none is more fascinating than the many worlds interpretation of quantum mechanics. As we settle into this chapter, imagine reality not as a single path, but as an ever-branching tree, each branch a universe of its own, born from the whispers of quantum possibility. The many worlds interpretation emerged in the late 1950s, proposed by a young physicist named Hugh Everett III, while he was still a doctoral student at Princeton University. At the time, quantum mechanics was already revolutionary but deeply puzzling to scientists. It described a world where particles could exist in multiple states simultaneously, where certainty gave way to probability, and where the very act of measurement seemed to collapse these multiple possibilities into a single reality. The standard view of quantum mechanics, known as the Copenhagen interpretation, suggested that particles exist as probability waves until measured, at which point they collapse into definite states. But Everett asked a simple yet profound question. What if the collapse never actually happens? What if, instead, reality itself branches to accommodate all possible outcomes? To understand this revolutionary idea, let us consider a simple quantum experiment. Imagine a single electron that can spin either up or down. According to quantum mechanics, until measured, the electron exists in a superposition of both states simultaneously, neither fully up nor fully down, but in a mysterious blend of both possibilities. When a scientist measures the electron, they will find it spinning either up or down, never both. The Copenhagen interpretation suggests that the act of measurement causes the electron's wave function to collapse into one state or the other. But Everett proposed something far more radical. He suggested that when measurement occurs, the universe splits into two parallel realities. In one universe, the scientist observes the electron spinning up. In the other universe, an identical scientist observes the same electron spinning down. Neither branch is more real than the other. Both continue to exist and evolve according to the same physical laws. The only difference is the outcome of that single quantum measurement, and crucially, the scientists in each branch have no way to detect or communicate with their counterparts in the other branch. Each experiences only their own reality, unaware of the split that has occurred. This process happens not just in laboratories but everywhere, Constantly, every time a quantum event occurs where multiple outcomes are possible, reality branches. Since quantum events happen billions upon billions of times each second throughout the universe, the branching would be essentially continuous and infinite. Each quantum choice point creates new universes, new realities flowing forward in parallel. Close your eyes for a moment and imagine a vast cosmic tree. You stand at the trunk in the present moment. Behind you stretches the single path of the past. But ahead of you, the tree branches and branches again, each fork representing a quantum choice point. Each branch a universe where one possibility becomes reality. In some branches, the differences from our world might be imperceptible, perhaps only the position of a few particles altered slightly. In others, these microscopic differences might cascade into larger and larger divergences over time. Quantum effects can be amplified. A particle taking one path rather than another might eventually influence which sperm reaches an egg, which person meets another, or which crucial decision gets made in a moment of historical importance. This means there might be branches where dinosaurs never went extinct because the asteroid that hit Earth was deflected by a quantum fluctuation. Branches where human history unfolded completely differently. Branches where you made different choices at key moments in your life. In the many worlds framework, all possibilities exist, somewhere in the vast branching structure of reality. What does this mean for our sense of self? If the many worlds interpretation is correct, there are countless versions of you experiencing different lives, making different choices, facing different circumstances. The version of you listening to these words right now is just one leaf on an infinite tree of possibilities. Yet each version feels unique, singular, the only you there is. The theory challenges our very notion of identity and consciousness. Are all these versions of you somehow connected? Do they share some essential quality of you-ness? Or is each truly separate, a unique consciousness walking its own path through its branch of reality? Some philosophers have suggested that consciousness might somehow navigate this branching structure, creating our subjective sense of a single timeline. Others propose that each branching creates genuinely separate consciousnesses, duplicates that diverge from the moment of splitting and never reconnect. The many worlds interpretation elegantly solves some of the deepest paradoxes in quantum mechanics. It removes the need for wave function collapse, that mysterious process where multiple quantum possibilities somehow become a single reality. In many worlds, all possibilities remain real, just in different branches of the universal wave function. It also addresses the measurement problem, the question of why observation seems to have a special role in quantum physics. In many worlds, observation is not special. It simply correlates the state of the observer with the state of the observed system, creating branches where each possible correlation exists. The theory faces criticisms, of course. Some scientists argue that it violates Occam's razor, the principle that simpler explanations are preferable. Is it simpler to propose one universe with mysterious quantum behavior or an infinite number of branching universes? Others question whether a theory that predicts parallel universes we can never observe or contact can truly be considered scientific. Yet the mathematics of many worlds is compelling in its simplicity. It takes the quantum wave equation and applies it consistently at all scales, without adding special rules for measurement or observation. It treats the entire universe, including observers, as one vast quantum system, evolving according to the same fundamental rules. As scientific theories go, the many worlds interpretation makes few assumptions beyond the mathematics of quantum mechanics that we already know works extremely well for describing the physical world. It simply takes those equations seriously, following them to their logical conclusion, even when that conclusion seems fantastically strange to our classical intuitions. If every quantum possibility branches reality, creating new universes where each outcome occurs, the implications are truly mind-boggling. The number of parallel universes would be not merely huge, but genuinely infinite, constantly multiplying as quantum events occur. Imagine the light from a distant star passing through space. Each photon, each particle of light, can take slightly different paths, creating quantum uncertainty in its exact trajectory. In many worlds, each possible path creates a new universe. Now multiply that by all the photons from all the stars in all the galaxies, plus all the other quantum events occurring everywhere. The branching becomes beyond comprehension. Yet according to proponents of many worlds, all of these branches are equally real. None is the main or original timeline. Each is simply one possibility playing out among infinite others. We perceive our branch as special only because we happen to be in it. The theory leads to fascinating philosophical questions about probability and decision-making. If all possibilities occur in some branch of reality, what does it mean to make a good or bad decision? No matter what you choose, some version of you will experience each possible outcome. Some philosophers have suggested that the many worlds interpretation changes how we should think about risk. If you face a decision with a 99% chance of success and a 1% chance of catastrophic failure, in many worlds, both outcomes will occur. Some versions of you will experience success, while others will face disaster. Should this change how you approach such decisions? Some argue that you should care about all future versions of yourself equally, and so should still choose the option that gives most of your future selves a positive outcome. Others suggest that the mere existence of branches where things go badly should make us more cautious about existential risks, events that could end human civilization or life on Earth. The many worlds interpretation also raises intriguing questions about free will and determinism. In one sense, it seems to restore a kind of freedom to a universe otherwise governed by physical law. All possibilities occur somewhere, so perhaps the future is not fixed, but contains all potential outcomes. Yet from another perspective, the branching itself follows strict quantum mechanical rules. The entire structure of branching universes would be mathematically determined by the universal wave function evolving according to fixed equations. Free will might be an illusion, a subjective experience of navigating branches whose structure was set from the beginning. Could these parallel branches ever communicate or interact? In the original formulation of many worlds, the answer is no. Once branches separate, they become effectively independent universes with no causal connection to each other. Information cannot pass between branches any more than information can travel faster than light within our universe. But some theoretical physicists have proposed modifications or extensions to the many worlds framework that might allow for subtle interactions between branches under special circumstances. These speculative ideas often involve quantum interference, the phenomenon where quantum waves can affect each other. Normally, when quantum branches separate, a process called decoherence quickly makes them unable to interfere with each other. Decoherence happens when quantum systems interact with their environment, causing quantum information to spread in a way that makes the branches distinctly separate. But what if, under certain rare conditions, branches could partially recohere? What if the walls between worlds became temporarily permeable, allowing whispers of information to pass through? This remains highly speculative, but it opens a theoretical window to the possibility of communication between parallel realities. Some researchers have suggested that certain anomalies in quantum experiments might be evidence of interference from parallel branches. Others propose that consciousness itself might have quantum properties that allow it to perceive or even influence this branching structure in subtle ways. These ideas remain at the fringes of physics, more philosophy than established science, but they illustrate the rich landscape of thought that many worlds has inspired. As we contemplate these vast branching realities, it is natural to wonder about our own place within them. If every possibility exists somewhere, what gives meaning to our choices? Why strive for one outcome over another if all outcomes happen anyway? Perhaps the answer lies in our local experience, in the reality we perceive around us. While all possibilities may exist across the multiverse, we only ever experience one branch at a time. The choices we make shape the branch we experience, the reality we live within. That local experience, that personal journey through one path in the quantum maze, still matters deeply to us as conscious beings. Or perhaps meaning comes from patterns that manifest across many branches. Maybe certain choices tend to lead to flourishing in most branches, while others lead to suffering. Maybe wisdom means learning to choose paths that benefit not just ourselves in this branch, but most versions of ourselves across the multiverse. As we come to the end of this chapter on the many worlds interpretation, take a moment to consider your own journey through the quantum branches of reality. Every moment, every decision, every quantum fluctuation may be creating new versions of you, exploring different paths through the infinite landscape of possibility. If every choice splits reality, could these branches ever touch? Could information ever flow between these parallel worlds? These questions lead us naturally to our next exploration, where we will examine the mysterious phenomenon of quantum entanglement and its potential to connect what seems forever separate. As you rest and reflect, imagine the countless other yous doing the same, listening to these same words in parallel realities, each experiencing their own thread in the vast cosmic tapestry. In the grand scheme of the multiverse, perhaps we are both many and one, separate yet connected through the underlying mathematics that shapes all branches of reality. If parallel universes exist, could they ever communicate with one another? To explore this profound question, we must first understand one of the most mysterious phenomena in quantum physics: entanglement, a connection that Albert Einstein famously called spooky action at a distance. Imagine two particles, perhaps two photons of light, created together in a single quantum event. According to quantum mechanics, these particles can become entangled, meaning their properties become correlated in ways that defy our classical intuition of how the universe works. When particles are entangled, they form a single quantum system, even if they later travel to opposite ends of the universe. Measure one particle, and you instantly know properties of the other, regardless of the distance separating them. This connection appears to transcend space itself, operating with no time delay, as if the particles were whispering secrets to each other across the cosmos. Let us explore a simple example to understand this remarkable phenomenon. Imagine two entangled electrons, with a property called spin. Quantum mechanics tells us that until measured, each electron exists in a superposition of spinning up and spinning down simultaneously. But these particular electrons are entangled in such a way that if one is measured and found to be spinning up, the other must be spinning down, and vice versa. Now imagine these electrons are separated by a vast distance, perhaps light years apart. An observer measures the first electron and finds it spinning up. At that very instant, the second electron, far across the universe, assumes the corresponding downspin state. This happens instantaneously, with no time for a signal to travel between them, even at the speed of light. This phenomenon deeply troubled Einstein and other physicists because it seemed to violate a fundamental principle: that nothing, not even information, can travel faster than light. How could the second particle know immediately what happened to the first? Einstein suggested that quantum mechanics must be incomplete. Perhaps there were hidden variables, properties determined at the creation of the particles that we simply could not detect. For decades, this remained a philosophical debate rather than an experimental question. But in 1964, a physicist named John Bell devised a mathematical framework that could distinguish between quantum mechanics and any theory involving hidden variables. Bell's inequality, as it became known, provided a way to test experimentally whether entanglement truly involved non-local connections or could be explained by local hidden variables. In the 1970s and 80s, experiments began to test Bell's inequality. The most famous were conducted by physicist Alain Aspect and his colleagues. Their results confirmed the predictions of quantum mechanics. Entanglement is real, and it involves correlations that cannot be explained by any theory involving only local interactions. The universe really does seem to permit non-local connections that act instantaneously across any distance. This has profound implications. It suggests that at some level, space itself may be an illusion. Two entangled particles separated by galaxies behave in some ways as if they occupy the same point. Distance becomes meaningless for certain aspects of their behavior. More recent experiments have only strengthened these conclusions. In 2015, scientists conducted what they called loophole-free tests of Bell's inequality, closing various technical gaps in earlier experiments. These tests showed beyond reasonable doubt that entanglement involves genuine non-locality. The universe permits instantaneous correlations across arbitrary distances. How does this relate to parallel universes? If entanglement can connect particles across space, could it perhaps connect them across universes as well? Could the mysterious non-locality of quantum physics extend not just through space, but through the boundaries between different branches of reality? Some theoretical physicists have proposed that entanglement might indeed provide a bridge between parallel universes. In these speculative models, particles in our universe might be entangled with their counterparts in parallel branches. While we could not directly observe these other universes, the behavior of entangled particles in our world might be subtly influenced by their connections to other branches of reality. Imagine two electrons created together, then separated by a quantum event that causes reality to branch. Each electron would exist in both branches, but in different states. The entanglement between these electrons would now span not just space, but the boundary between universes. Measuring one electron in our branch might, in theory, be correlated with the state of its counterpart in the parallel branch. Of course, verifying such ideas experimentally presents enormous challenges. How could we detect the influence of a parallel universe that we cannot directly observe? Scientists have proposed various indirect tests, looking for subtle anomalies in the behavior of entangled particles that might suggest influences from beyond our own branch of reality. One framework for understanding quantum mechanics, known as the relational interpretation, suggests that quantum states are not absolute but exist only in relation to other systems. In this view, reality itself emerges from a network of relationships between quantum systems. Such a perspective might allow for information to exist not within any single universe, but in the relationships between universes, encoded in entanglement connections that transcend the boundaries between branches. Another approach comes from quantum decoherence theory, which explains how quantum systems lose their wave-like properties and begin to behave classically when they interact with their environment. Decoherence is usually seen as a one-way process that permanently separates quantum branches. But some theorists suggest that under certain rare conditions, branches that have separated might partially recohere, allowing for faint echoes of information to pass between them. Recent experiments with quantum computing have demonstrated that under carefully controlled conditions, scientists can reverse decoherence and recover quantum information that seemed lost. While these experiments are far from proving communication between parallel universes, they show that quantum information can be more resilient and interconnected than previously thought. Quantum entanglement also relates to another fascinating concept: quantum teleportation. Despite its science fiction-sounding name, quantum teleportation is a well-established laboratory technique that uses entanglement to transfer quantum states from one particle to another instantaneously, regardless of the distance between them. The process requires both quantum and classical channels of communication. The sender and receiver must each have one member of an entangled pair of particles, and the sender must also transmit some classical information to the receiver. Using this combination of quantum entanglement and classical information, the quantum state of a third particle can be perfectly recreated at the receiver's location. Crucially, quantum teleportation does not transmit matter or energy, only information. The original quantum state is destroyed in the process, preserving a fundamental principle called the no-cloning theorem. which states that it is impossible to create a perfect copy of an unknown quantum state. Could similar principles allow for information transfer between parallel universes? Perhaps the mathematics of quantum teleportation might be extended to describe theoretical connections between different branches of reality. Some speculative models suggest that certain quantum phenomena in our universe might be explained as the results of teleportation, like processes involving parallel branches. One of the most intriguing connections between entanglement and parallel universes comes from a concept called quantum discord. Beyond entanglement, quantum discord measures more subtle quantum correlations that can exist between systems. Some physicists have suggested that while strong entanglement between universes might be quickly destroyed by decoherence, weaker forms of quantum correlation, measured by quantum discord, might persist longer and allow for faint traces of information to pass between branches. Another relevant concept is quantum Darwinism, which explains how classical reality emerges from quantum foundations through a process analogous to natural selection. As quantum systems interact with their environment, certain states prove more robust and leave multiple imprints on surrounding systems. These states effectively compete for stability, with the most resilient becoming the classical reality we observe. In the context of parallel universes, quantum Darwinism suggests that branches of reality themselves might compete or interact in subtle ways, with information from some branches influencing others through persistent quantum correlations. The boundaries between worlds might be fuzzier and more permeable than we imagine. A more exotic possibility involves quantum tunneling between universes. In standard quantum mechanics, particles can sometimes tunnel through energy barriers that would be impassable according to classical physics. Some speculative theories extend this concept to the multiverse, suggesting that information or influence might occasionally tunnel between parallel realities, creating faint connections between otherwise separate branches. Recent developments in quantum gravity theories offer additional perspectives on potential communications between universes. In loop quantum cosmology, for instance, the Big Bang is replaced by a Big Bounce, where a previous universe contracted and then expanded again to form our own. In such models, information might be transmitted across the bounce, allowing one universe to influence its successor. String theory and its extension, M-theory, suggest that our universe might be a three-dimensional membrane or brane floating in a higher dimensional bulk space, potentially alongside other brane universes. In these models, gravity might leak between branes, creating subtle influences that could, in principle, carry information between parallel universes. The holographic principle, which proposes that the information contained in a volume of space can be represented on a boundary enclosing that region, offers yet another framework for thinking about universe communication. If multiple universes share holographic boundaries, information encoded on these boundaries might create correlations between otherwise separate realities. While these ideas remain highly speculative, they illustrate how quantum entanglement and non-locality open conceptual doors to the possibility of connections between parallel universes. The mathematics that successfully describes quantum phenomena in our universe often hints at deeper structures that might transcend the boundaries of any single reality. Of course, we should maintain scientific caution. Many of these ideas have not yet reached the stage where they can be experimentally tested. Some may remain forever in the realm of mathematical possibility rather than physical reality. Others might eventually lead to testable predictions that could confirm or refute the existence of connections between universes. For now, quantum entanglement remains one of the most profound mysteries in physics, a phenomenon that even after a century of study continues to challenge our understanding of space, time, and reality itself. As physicist Richard Feynman famously remarked, "If you think you understand quantum mechanics, you don't understand quantum mechanics." Perhaps the most remarkable aspect of quantum entanglement is how it has moved from a philosophical puzzle to an applicable technology. Today, researchers around the world are developing quantum networks that use entanglement to transmit information with perfect security. Quantum computers leverage entanglement to perform calculations impossible for classical machines. What was once a counterintuitive curiosity has become the foundation for a technological revolution. As you contemplate these mysterious quantum connections that transcend space, consider how they might also transcend the boundaries between realities. If entanglement can instantly connect particles across the vastness of our universe, might it also connect them across the perhaps even vaster gulf between parallel universes? Imagine entangled particles as cosmic pen pals, exchanging whispers of information not just across space, but across the boundaries of reality itself. These whispers might be faint, hard to detect amid the noise of our quantum world, but they could represent the first tenuous lines of communication in a conversation between universes. As we drift towards sleep, let these quantum possibilities float in your mind. The mathematics of entanglement points to a universe, perhaps a multiverse, more richly connected than our everyday experience suggests. Space may be an illusion, distance meaningless at the quantum level, and in that deeper reality, the walls between universes might be thinner and more permeable than we ever imagined. Entanglement defies distance, but does it defy reality itself? This question leads us naturally to our next exploration, where we will examine theoretical cosmic bridges that might span not just space, but the gaps between universes themselves. Perhaps the most profound journey we can take is one that traverses not just space, but reality itself. As we contemplate the vast expanse of our universe, a tantalizing question emerges. If parallel universes exist beyond our own, could there be passageways connecting these separate realities? The concept of wormholes offers us a glimpse into this possibility, a theoretical bridge between worlds that might allow communication across the cosmic divide. Imagine for a moment that space-time is not rigid but flexible, like a vast cosmic fabric that can be folded and connected at distant points. This is the fundamental premise behind wormholes, theoretical tunnels through the very structure of reality. Rather than traveling the long way around through normal space, a wormhole would provide a shortcut, a cosmic passageway linking distant regions of our universe, or potentially connecting parallel universes altogether. The mathematics behind wormholes emerged from Einstein's theory of general relativity, which describes gravity not as a force, but as a curvature of space-time caused by mass and energy. In 1916, just months after Einstein published his groundbreaking work, Austrian physicist Ludwig Flamm discovered that the equations allowed for a theoretical connection between two different points in space-time. This concept was later expanded by physicist Albert Einstein and his colleague Nathan Rosen in 1935, leading to what we now call an Einstein-Rosen bridge. Picture two sheets of paper, each representing a separate universe or distant regions of our own universe. If we bring these sheets together and connect them with a tube, we create a visual representation of a wormhole. This tunnel would theoretically allow matter and information to travel between points that might otherwise be impossibly far apart. But the mathematics of general relativity suggests something even more fascinating. These wormholes might not just connect distant regions within our universe, but could potentially serve as gateways between parallel universes within a larger multiverse structure. If the many worlds interpretation of quantum mechanics is correct, and reality branches at every quantum event, wormholes might represent rare connections between these branching realities. What would it mean to traverse such a cosmic bridge? The journey through a wormhole would be unlike any voyage we could imagine. You wouldn't experience traveling through vast distances of normal space. Instead, you would enter the wormhole's mouth and emerge almost instantaneously from its exit, perhaps in another universe entirely, with different physical laws or alternate versions of our own reality. However, the existence of traversable wormholes faces significant theoretical challenges. The mathematics of general relativity indicates that wormholes would be extremely unstable, collapsing instantly before anything could pass through them. For a wormhole to remain open long enough for communication or travel, it would require something exotic, a substance with negative energy density that physicists call exotic matter. Exotic matter is not the dark matter that astronomers observe influencing galaxies. Rather, it's a hypothetical substance with properties that seem to violate our understanding of physics. It would need to exert negative pressure and have negative energy density, effectively pushing outward against the natural tendency of the wormhole to collapse. While quantum physics does allow for negative energy states in certain contexts, such as the Casimir effect, whether enough exotic matter could exist to stabilize a macroscopic wormhole remains highly speculative. Despite these challenges, the possibility of wormholes connecting parallel universes continues to captivate both physicists and the public imagination. If such connections exist, they might allow for communication between worlds that have branched from our own. Messages or signals might traverse these cosmic bridges, carrying information between realities that otherwise would remain forever separate. Even more intriguing is the connection between wormholes and time. Since Einstein's theories link space and time inseparably as space-time, wormholes might not just be shortcuts through space, but potentially through time as well. Some theoretical models suggest that wormholes could connect not just different locations, but different times, raising the specter of time travel and all its paradoxes. Imagine a wormhole with one mouth in our universe in the year 2025 and another mouth in a parallel universe where events unfolded slightly differently, perhaps in their equivalent of 1995. Such a connection would not only bridge different realities, but different time periods, creating a passage through which information could flow between temporally separated worlds. This brings us to the grandfather paradox, a classic thought experiment in time travel. What would happen if you traveled back in time and prevented your own grandfather from meeting your grandmother? If you were never born, how could you have traveled back in time in the first place? When we consider wormholes connecting parallel universes, this paradox takes on new dimensions. Some physicists propose that nature might prevent such paradoxes through what's called the Novikov self-consistency principle. This principle suggests that the probability of events causing paradoxes would be zero. In other words, something would always prevent paradoxical outcomes, preserving the consistency of space-time. Perhaps you might try to change the past, but would be prevented by coincidences or physical limitations that ensure history unfolds as it already has. Alternatively, the many worlds interpretation offers another resolution. When you travel back in time, you might actually be entering a parallel branch of reality. Any changes you make would affect this alternate timeline, not your original one. This would mean that wormholes connecting parallel universes might facilitate communication between branches of reality without creating paradoxes. Russian physicist Igor Novikov suggested that wormholes might be subject to a principle of self-consistency. This would mean that any signal or matter that travels through a wormhole to the past would only be able to do things that would not change established history. Causality would be preserved not through some mysterious force preventing certain actions, but through the logical structure of events themselves. While traversable wormholes remain theoretical, astronomers do observe phenomena that bear some resemblance to wormhole physics. Black holes, those cosmic objects with gravity so intense that not even light can escape, share mathematical similarities with wormholes. Some physicists have suggested that black holes might actually be one end of a wormhole, with the other end manifesting as a white hole in another region of space-time or even another universe entirely. A white hole would be the theoretical opposite of a black hole, expelling matter and energy rather than consuming it. Nothing could enter a white hole, just as nothing could escape a black hole. If black holes and white holes are connected by wormholes, they might represent cosmic drainage systems, with matter falling into black holes in our universe emerging from white holes in parallel universes. This concept formed the basis for theoretical physicist Kip Thorne's work on wormholes, which later inspired the film Interstellar. Thorne proposed that a sufficiently advanced civilization might be able to capture and enlarge a naturally occurring wormhole, stabilizing it with exotic matter to create a traversable passage between distant points in space-time. The energy requirements for such an endeavor would be staggering, far beyond our current technological capabilities. Creating and stabilizing a wormhole large enough for even a single particle to pass through would require energy equivalent to that of many stars. For a wormhole large enough for a human to traverse, the energy needs would be astronomical, perhaps requiring the power output of an entire galaxy. Yet if parallel universes can communicate through wormholes, we might not need to create them ourselves. Perhaps they occur naturally, tiny quantum fluctuations in the fabric of space-time that briefly connect different universes before collapsing. These quantum wormholes might be too small and short, lived for macroscopic objects to pass through, but they could potentially allow for the exchange of information or energy between universes. This raises an intriguing possibility. If quantum wormholes naturally connect parallel universes, could this explain some of the strange findings in quantum physics? The phenomenon of quantum entanglement, where particles remain connected regardless of distance, has puzzled physicists for decades. Some have speculated that entangled particles might be connected by microscopic wormholes, their apparent action at a distance actually facilitated by these shortcuts through spacetime. Physicist Juan Maldacena and Leonard Susskind proposed what they called ER equals EPR, suggesting that entangled particles, described by the Einstein-Podolsky-Rosen paradox, might be connected by Einstein-Rosen bridges, another name for wormholes. This would mean that the seemingly instantaneous correlation between entangled particles could be explained by wormhole connections, unifying quantum mechanics and general relativity in an elegant way. If this hypothesis is correct, then quantum entanglement might represent a form of communication between parallel universes. Every entangled particle in our universe might have a counterpart in another universe, their properties linked across the cosmic divide. When we measure an entangled particle here, we might be inadvertently sending a signal to its partner in another reality. The implications of such communication would be profound. It would suggest that parallel universes are not entirely separate, but form an interconnected web of reality, with information flowing between branches through quantum channels. Our universe would not be isolated, but part of a larger cosmic conversation, exchanging quantum whispers with alternate realities through the hidden language of entanglement. As we contemplate these possibilities, we must acknowledge the vast gap between theoretical physics and experimental confirmation. Wormholes remain mathematical constructs, solutions to Einstein's field equations that may or may not have physical reality. Detecting a wormhole, let alone one connecting to a parallel universe, lies beyond our current technological capabilities. Yet the absence of evidence is not evidence of absence. Throughout history, many theoretical concepts in physics seemed impossibly speculative until technology advanced enough to test them. The existence of black holes was once considered mathematical curiosity before astronomical observations confirmed their reality. Perhaps wormholes connecting parallel universes await similar confirmation, hidden in cosmic phenomena we have yet to fully understand. If wormholes do provide bridges between universes, what might pass through them? Information seems the most likely candidate, quantum signals traversing the cosmic divide. But information is not just abstract data, it's the fundamental currency of reality itself. In quantum physics, information is conserved, meaning it cannot be destroyed, only transformed. This conservation law might apply across the multiverse, with information flowing through wormholes as part of some greater cosmic balance. As we move beyond the concept of wormholes, our journey takes us to another fascinating frontier of theoretical physics, the realm of brane cosmology. This perspective sees our universe not as all that exists, but as a mere membrane floating in a higher dimensional space alongside countless other universe membranes. In this view, parallel universes might be literally parallel, separated from our own, not by vast distances, but by the gap between dimensions. Brane cosmology emerges from string theory. a framework that attempts to unify the four fundamental forces of nature. In string theory, the basic building blocks of reality are not point-like particles, but tiny vibrating strings of energy. These strings vibrate in different patterns to create the particles we observe, like the different notes played on a violin string. But string theory requires more dimensions than the four we experience, with the extra dimensions curled up to microscopic size or extending beyond our perception. In the brain world scenario, our universe exists as a three-dimensional membrane, or brain, floating in a higher dimensional space called the bulk. Imagine our universe as a sheet of paper in a stack of many sheets, each representing a separate universe. These universe brains might be separated by distances measured not in light years, but in the units of an extra dimension we cannot directly observe. The particles and forces we experience, such as photons and the electromagnetic force, would be confined to our brain, explaining why we don't observe the extra dimensions in everyday life. These particles and forces can be thought of as strings with their endpoints anchored to our brain, unable to leave our universe. But gravity, according to some versions of string theory, might be different, represented by closed loops of string that could travel between brains, leaking into the bulk beyond our universe. This would potentially explain why gravity seems so much weaker than the other fundamental forces. Its strength might be diluted by spreading into extra dimensions, with only a fraction of its influence felt in our universe. If gravity can indeed traverse the bulk between brains, it raises the possibility that parallel universes might interact gravitationally, their masses pulling on each other across the dimensional divide. The ekpyrotic universe theory, developed by physicists Paul Steinhardt and Neil Turok, suggests that our universe's Big Bang might have resulted from a collision between two universe brains. In this scenario, the tremendous energy released when these brains collided manifested as the hot, dense state from which our universe expanded. If this is true, then our universe's very existence might be the result of communication between parallel realities, a cosmic conversation written in the language of energy and matter. These brain collisions might happen repeatedly throughout the greater multiverse, with each collision generating a new Big Bang and a new universe cycle. Our universe might be just one expansion phase in an eternal series of collisions and expansions, a cosmic rhythm playing out across dimensions we cannot directly perceive. But could signals intentionally pass between these brain worlds? Some theoretical models suggest that under certain conditions, particles or forces might transfer between adjacent brains. These transfers might be extremely rare and subject to quantum probability, but they could represent a form of communication between parallel universe brains. If our universe brain is indeed floating in a higher dimensional bulk alongside other brains, there might be regions where these brains come close enough for interaction. These regions could serve as cosmic exchange points, where information or energy might transfer between parallel universes under specific conditions. The evidence for such interactions would be subtle and challenging to detect. Scientists have proposed looking for anomalies in cosmic rays, particles from space that strike Earth's atmosphere with enormous energy. If some of these particles originated from another brain world, they might display energy signatures inconsistent with particles accelerated by known cosmic processes within our universe. Similarly, unusual patterns in gravitational waves, ripples in spacetime detected by instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, might signal gravitational influences from parallel brains. As our detection capabilities improve, we might find the first empirical evidence for brain-world interactions hiding in these cosmic messengers. The implications of brain cosmology extend beyond physics into the philosophical realm. If our universe is just one membrane in a vast multidimensional space, our concept of reality must expand accordingly. The cosmos would not be limited to what we can observe through telescopes, but would include countless other universes, perhaps with different physical laws, existing in parallel to our own. This perspective transforms our understanding of cosmic origins. Rather than our universe emerging from a singular Big Bang event, it might be part of an eternal brain dance, colliding and separating in endless cycles. Our existence would be one movement in this greater cosmic symphony, connected to parallel realities through the shared higher dimensions of the bulk. The brain world scenario also offers new perspectives on dark matter and dark energy, those mysterious components that seem to make up most of our universe's mass energy content. Perhaps dark matter particles are actually ordinary matter on a parallel brane, their gravitational influence reaching across the dimensional gap to affect our universe. Dark energy, the force accelerating our universe's expansion, might similarly represent an influence from beyond our brain, a pressure exerted by the higher dimensional bulk or neighboring branes. This brings us to the question of what might happen if brains do communicate or interact. Unlike wormhole connections, which might allow for direct passage between universes, brain interactions would likely be more subtle, manifesting as influences rather than direct exchanges. Gravity might pull across the dimensional divide, or exotic particles might occasionally transfer between adjacent branes. If parallel branes do interact gravitationally, this might leave detectable signatures in the cosmic microwave background radiation, the afterglow of the Big Bang that permeates our universe. Unusual patterns or anomalies in this radiation might indicate the gravitational influence of neighboring universe branes, their masses tugging on our space-time across the dimensional gap. More dramatically, if brane collisions generate Big Bang events, then the beginning of our universe might itself be a record of communication between parallel realities. The particular pattern of temperature fluctuations in the cosmic microwave background might carry information about the brane collision that spawned our universe, a message from another reality encoded in the very birth of our cosmos. As we reach deeper into the theoretical framework of parallel universes, we encounter another fascinating concept that may help us understand the nature of reality and potential communication between universes. This is the holographic principle, a radical idea suggesting that our three-dimensional reality might be encoded on a two-dimensional boundary, like a hologram projected from a flat surface. The holographic principle emerged from studies of black holes and their entropy. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy is proportional not to its volume, as one might expect, but to the surface area of its event horizon. This strange finding suggested that all the information about what falls into a black hole is somehow encoded on its two-dimensional boundary. Physicist Leonard Susskind, Juan Maldacena, and others extended this concept to propose that our entire universe might function similarly, with all the information about our three-dimensional reality encoded on a distant two-dimensional boundary. This would mean that the world we experience, with its apparent depth and volume, might be a projection of information stored on a cosmic surface, much like a hologram creates the illusion of three dimensions from a flat image. The mathematics supporting this view comes from string theory and a relationship called the ADS-CFT correspondence, a connection between a gravitational theory in a space with negative curvature called anti-de Sitter space and a quantum field theory called conformal field theory that would exist on the boundary of this space. While our universe does not appear to be an anti-de Sitter space, this mathematical relationship provides a concrete example of how the holographic principle might work. If our universe is indeed holographic, with all its information encoded on a boundary, this has profound implications for understanding parallel universes and potential communication between them. The boundary containing our universe's information might be just one of many such boundaries, each encoding a different universe in the multiverse. These boundaries might not be completely separate. Just as holograms can be overlaid to create interference patterns, the boundaries encoding different universes might interact or overlap in certain regions. These overlaps could represent areas where information transfers between parallel universes, creating connections or communications across the multiverse. Imagine our universe as a vast cosmic hologram, its three-dimensional reality projected from encoded information on a distant boundary. Now imagine another universe as a separate hologram, with its own boundary encoding its unique reality. If these boundaries come into contact or overlap, the interference patterns created might manifest as anomalies or unusual phenomena in both universes, signals crossing the divide between parallel realities. The holographic principle also connects to quantum entanglement in intriguing ways. In a holographic universe, entanglement between particles might represent connections in the underlying code on the boundary. These connections could potentially extend across different universe boundaries, creating entanglement between particles in separate universes. If measured, such cross-universe entanglement would constitute a form of communication between parallel realities. Some theoretical physicists have proposed that the holographic principle might help resolve the black hole information paradox, the puzzle of what happens to information that falls into a black hole. If black holes are truly holographic, with all their information encoded on their event horizons, then this information is not truly lost. Similarly, information that appears to be lost between parallel universes might actually be preserved on their holographic boundaries, potentially accessible through the right mathematical transformations. The holographic view of the universe also offers new perspectives on the nature of space and time themselves. If our three-dimensional reality is a projection from a two-dimensional boundary, then space as we experience it is not fundamental, but emergent, a consequence of how information is organized on the boundary. Time might similarly emerge from the evolution of this information, rather than being a basic component of reality. This suggests that parallel universes might not be separated by space in the conventional sense. Instead, they might be different informational states or configurations on their respective boundaries. Communication between these universes would not involve traversing physical distance, but rather transferring information between these boundary states. The mathematics of holography also suggests that universes with different physical laws might be connected through transformations of their boundary information. A universe with one set of physical constants might be equivalent to another universe with different constants, but organized in a mathematically related way on its boundary. This would mean that parallel universes are not just similar versions of our reality, but could include worlds with fundamentally different physics, all connected through the mathematics of their holographic descriptions. If the holographic principle is correct, and our universe is encoded on a boundary, we might ask where this boundary is located. The answer might be that it exists at the edge of our observable universe, or perhaps at the beginning of time, at the Big Bang itself. Alternatively, the boundary might exist in a higher dimensional space beyond our direct perception, accessible only through the mathematics of string theory and quantum gravity. Regardless of where this boundary might be, the holographic principle transforms our understanding of reality and the potential for communication between parallel universes. It suggests that universes are not separate bubbles floating in some greater space, but interconnected informational structures, their boundaries potentially overlapping or interacting in ways that allow for the exchange of information. This view also raises the possibility that we might someday learn to decode and manipulate the holographic information that defines our reality. A sufficiently advanced civilization might discover how to read the cosmic hologram, accessing information about parallel universes encoded at the boundaries of our own. This would represent a form of communication with parallel realities, not through physical travel, but through information processing, reading the code that defines the multiverse. As we consider these theoretical frameworks, from wormholes to brain worlds to the holographic principle, we find ourselves at the frontier of physics, where mathematics stretches our conception of reality. These models offer different perspectives on how parallel universes might exist and potentially communicate, each with its own implications and challenges. Wormholes present the possibility of direct connections, tunnels through space-time, that might allow matter or information to pass between separate universes. Brain cosmology suggests parallel universes might exist as membranes floating in higher dimensions, occasionally interacting through collisions or gravitational influence. The holographic principle proposes that universes might be encoded on boundaries, with information potentially transferring where these boundaries overlap or interact. While these frameworks differ in their details, they share a common theme: the possibility that parallel universes are not entirely separate, but connected through various mechanisms. Whether through wormholes, brain interactions, or holographic boundaries, information might flow between realities, creating a cosmic conversation across the multiverse. As we continue to explore these possibilities, we must acknowledge the vast gap between theoretical physics and experimental confirmation. The mathematics suggesting parallel universes and potential communication between them remains largely speculative, awaiting empirical evidence that might confirm or challenge these ideas. Yet the absence of evidence is not evidence of absence. Throughout history, many theoretical concepts in physics seemed impossibly speculative until technology advanced enough to test them. From the existence of atoms to the reality of black holes, scientific understanding has often progressed from mathematical conjecture to confirmed phenomena as our observational capabilities improved. Perhaps evidence for parallel universes and communication between them awaits discovery in cosmic phenomena we have yet to fully understand. Anomalies in the cosmic microwave background, unusual patterns in gravitational waves, or quantum effects that defy conventional explanation might hold clues to the greater multiverse beyond our observable reality. As our journey through theoretical physics continues, we find ourselves contemplating questions that bridge science and philosophy. If parallel universes exist and somehow communicate, what does this mean for our understanding of reality? Are we part of a vast cosmic conversation, our universe exchanging quantum whispers with alternate realities through wormholes, brain interactions, or holographic connections? These questions lead us beyond physics into the realm of consciousness and meaning. If parallel universes communicate, might conscious beings in these separate realities somehow sense or perceive these connections? Could our dreams, intuitions, or flashes of seeming impossible knowledge be echoes of information seeping through from parallel selves in alternate universes? Such speculation takes us to the edge of science and beyond, into realms where physics meets philosophy and even spirituality. Yet the mathematics suggesting parallel universes and potential connections between them remains firmly grounded in our best theoretical frameworks, from general relativity to quantum mechanics to string theory. As we continue our exploration, we turn our attention to more concrete proposals for how we might detect or even facilitate communication between parallel universes. Scientists have proposed various experimental approaches that might reveal evidence of a multiverse or even allow for the deliberate exchange of information between universes. These theoretical models of communication represent the next frontier in our journey through the mysteries of parallel universes. Science pushes boundaries, but nature guards its secrets. The cosmic conversation we seek to join may be happening all around us, in quantum fluctuations and gravitational waves, in the subtle patterns of subatomic particles and the vast structures of galaxies. Our challenge is to learn the languages of this conversation, to recognize the signals of parallel universes against the cosmic background noise of our own reality. As we contemplate these possibilities, we must maintain both scientific rigor and imaginative openness. The universe has repeatedly proven stranger than we imagined, revealing new layers of reality as our understanding deepens. Parallel universes and communication between them may seem like science fiction today, but they represent serious hypotheses within theoretical physics, mathematical possibilities that await experimental investigation. Whether through wormholes spanning the cosmic divide, brain interactions across higher dimensions, or information transfer through holographic boundaries, the possibility of communication between parallel universes offers a profound expansion of our cosmic perspective. It suggests that our reality is not isolated, but part of a greater conversation, a dialogue of universes speaking in the language of physics across the multiversal divide. As we venture deeper into the mysteries of parallel universes, we must consider not just their existence, but the theoretical frameworks that might allow for actual communication between these separate realities. Scientists and mathematicians have proposed various models suggesting how information might travel between universes, each with its own fascinating implications and challenges. Quantum interference represents one of the most promising avenues for potential multiverse communication. The famous double-slit experiment demonstrates how particles can interfere with themselves, suggesting they travel through multiple paths simultaneously. Some physicists propose that these interference patterns might actually result from particles interacting with their counterparts in parallel universes. Quantum physicist David Deutsch, a pioneer of quantum computing, has suggested that quantum computers might harness the processing power of their counterparts in parallel universes. When a quantum computer performs calculations using superpositions of quantum bits or qubits, it might be distributing the computational load across multiple versions of itself in the multiverse. The results we observe would then represent a kind of communication between these parallel quantum computers, with information flowing between universes through quantum channels. This perspective transforms our understanding of quantum computation. The exponential speed-up offered by quantum algorithms might not come from a single computer in our universe, but from countless computers working in parallel across the multiverse. Each time we run a quantum algorithm, we might be initiating a vast conversation between universes, their collective computational power contributing to the solution we observe in our reality. Imagine a quantum computer as a device that sends messages to and receives responses from countless parallel versions of itself. When we measure the output, we are essentially receiving the collective answer from this multiversal network. This would represent a form of communication not designed by humans, but inherent in the quantum mechanical nature of reality itself. The mathematics supporting these ideas emerges from Hugh Everett's many worlds interpretation of quantum mechanics. Everett proposed that when quantum measurements occur, reality branches into multiple versions, each representing a different possible outcome. Rather than wave function collapse occurring, all possibilities continue to exist in separate branches of reality. These branches do not collapse back together, but continue to evolve independently. Yet quantum interference suggests these branches are not entirely separate. The mathematics of quantum mechanics shows that particles in superposition states behave as if they interact with themselves along different possible paths. If these paths represent different branches of reality, then interference represents a form of communication between these branches, information leaking between parallel worlds that emerged from the same quantum event. Decoherence, the process by which quantum systems lose their coherence through interaction with their environment, places limitations on these potential communications. As quantum systems entangle with their surroundings, the clean superpositions that might allow for multiverse communication become increasingly complex and diffuse. This process happens extremely rapidly for macroscopic objects, explaining why we don't observe quantum effects in everyday life and potentially limiting the bandwidth of any communication channel between universes. However, carefully isolated quantum systems can maintain coherence for longer periods, preserving the potential for multiverse communication. Advances in quantum technologies have allowed scientists to maintain quantum coherence in increasingly large systems, from individual atoms to small molecules and even tiny visible objects. As these technologies improve, we might be able to create more robust channels for potential communication with parallel realities. Another theoretical avenue for multiverse communication involves cosmological natural selection, a concept proposed by physicist Lee Smolin. This theory suggests that black holes might give birth to new universes, with each universe's physical laws slightly modified from its parent universe. Those universes with physical laws that maximize black hole production would produce more offspring universes, leading to an evolutionary process across the multiverse. If this theory is correct, information might pass from parent to child universes through the black hole creation process. While this would not allow for two-way communication between existing parallel universes, it would represent a form of one-way information transfer across generations of universes. Our universe's physical laws might themselves be messages from a parent universe, optimized through a cosmic evolutionary process for black hole production and universe generation. Some physicists have even proposed that intentional messages might be encoded in the physical constants of child universes. An advanced civilization in a parent universe might find ways to slightly modify the black hole formation process, to encode information in the fundamental constants or initial conditions of the baby universes they create. This would represent a form of intergenerational communication across the multiverse, messages passed from creator universes to their cosmic offspring. While such communication would not allow for dialogue between existing parallel universes, it raises the fascinating possibility that our own universe's fundamental constants might contain encoded messages from a creator universe. The specific values of constants, like the strength of gravity or the mass of the electron, might not be random, but carefully tuned to communicate information across the multiverse. Other theoretical models focus on potential communication through higher dimensions. String theory suggests our universe exists as a three-dimensional brain within a higher dimensional bulk. If parallel universe brains float within this same bulk, signals might travel through the higher dimensions to reach other universes. Gravitational waves, ripples in spacetime recently detected by observatories like LIGO, might have counterparts that propagate through higher dimensions. These bulk gravitational waves could potentially carry information between parallel universe brains, creating subtle signals detectable as anomalies in our universe's gravitational wave observations. Some models propose that under specific conditions, particles called moduli might traverse the bulk between brains, carrying information between parallel universes. These particles would interact very weakly with ordinary matter, making them difficult to detect, but they could create subtle effects that might be measurable with sufficiently sensitive equipment. Mathematics also offers insights into potential multiverse communication through the concept of cosmic topology. Just as a video game screen wraps around when a character moves off one edge and appears on the opposite side, our universe might have a non-trivial topology that connects distant regions. If this topology extends to the multiverse, it might create natural connections between otherwise separate universes. Computer simulations provide another framework for understanding multiverse communication. If our universe is a simulation, as some philosophers and physicists have proposed, then parallel universes might be other simulations running on the same underlying computational substrate. Communication between these simulations might occur through the equivalent of API calls or shared memory, manifesting in our reality as seemingly causal connections or synchronicities. The possibility of multiverse communication also emerges in loop quantum cosmology, where the Big Bang represents a bounce from a previous universe's contraction. In this model, information from the previous universe cycle might survive the bounce process, creating a form of temporal communication across successive universe cycles. Our universe might carry echoes of previous cosmic cycles, messages from universes that existed before our own Big Bang. As we consider these theoretical models, we must acknowledge the significant challenges facing any attempt at multiverse communication. The signal-to-noise ratio presents perhaps the greatest obstacle. Any message from a parallel universe would need to be distinguished from the vast background noise of our own universe's natural processes. This would require identifying patterns that could not occur naturally and could only represent intentional communication. Energy requirements present another major challenge. Creating signals powerful enough to traverse the barriers between universes would likely require enormous energy, perhaps beyond what any civilization could harness. Even detecting such signals would demand extremely sensitive equipment, able to distinguish the subtle effects of cross-universe communication from natural phenomena. Finally, the bandwidth of any communication channel between universes might be severely limited. Quantum decoherence, dimensional barriers, or the fundamental structure of reality itself might restrict the amount and fidelity of information that could pass between parallel worlds. Messages might be limited to simple binary signals rather than rich data streams. Despite these challenges, the theoretical possibility of multiverse communication continues to inspire both scientific research and philosophical inquiry. The mathematics suggesting connections between parallel realities emerges not from fringe theories, but from our most successful physical frameworks, from quantum mechanics to relativity to string theory. While experimental confirmation remains elusive, the theoretical foundations for multiverse communication grow increasingly sophisticated. As we ponder these scientific possibilities, we must also consider their profound philosophical and existential implications. What would it mean for humanity if we confirmed the existence of parallel universes in communication with our own? How would this transform our understanding of reality, consciousness, and our place in the cosmos? The confirmation of parallel universes would fundamentally alter our cosmological perspective. Throughout history, humanity has experienced a series of great demotions, from believing Earth was the center of the universe to recognizing it as one planet among billions in one galaxy among billions. Confirming the multiverse would represent another such demotion, revealing our universe as just one reality among countless others. Yet this expanded perspective need not diminish humanity's significance. Just as biodiversity on Earth represents an enrichment rather than a diminishment of life, cosmic diversity across the multiverse might represent an enrichment of reality itself. Our universe, with its particular constants and laws, might be unique and precious precisely because it exists alongside countless different realities. The philosophical implications extend to our concepts of identity and selfhood. If the many worlds interpretation is correct, then each quantum decision point spawns new branches of reality, with different versions of ourselves pursuing different paths. These parallel selves would share our history up to the branching point, but would subsequently diverge, making different choices and experiencing different consequences. This raises profound questions about personal identity. If countless versions of you exist across the multiverse, each experiencing different lives resulting from different choices, which version represents the true you? Are you a single consciousness, somehow spread across multiple branches of reality? Or are you defined specifically by the branch you currently experience? Some philosophers propose that consciousness might exist across multiple branches simultaneously, with our subjective experience somehow integrating information from parallel versions of ourselves. This perspective aligns with quantum theories of consciousness that suggest our awareness might emerge from quantum processes in the brain that sample multiple branches of reality. Others argue that each branch contains a separate consciousness, with no awareness of its parallel counterparts. In this view, the you experiencing this particular branch of reality has no direct access to the experiences of your parallel selves in other universes, even though these parallel selves exist as surely as you do. Communication between parallel universes would transform these philosophical questions into empirical ones. If we could exchange information with parallel branches of reality, we might learn about the roads not taken, the consequences of different choices, the lives our parallel selves have lived. This would provide unprecedented insight into causality, choice, and the nature of possibility itself. The implications for free will and determinism would be equally profound. Does the existence of all possible branches mean that free will is an illusion, with every possible choice predetermined to occur in some branch of reality? Or does it actually validate free will by ensuring that every possible choice we might make actually does get made somewhere in the multiverse? Some philosophers argue that the multiverse view actually enhances meaning by ensuring that all possibilities are explored. Nothing is truly lost or wasted because every potential path is actually taken in some branch of reality. Others counter that this diffuses meaning by making every choice simultaneously consequential and inconsequential, since all options are realized somewhere. The existential weight of our decisions might be transformed if we knew parallel versions of ourselves were making different choices in other branches of reality. Would this knowledge liberate us from the burden of what might have been, knowing that somewhere else it actually is? Or would it heighten our sense of responsibility to this particular branch, this specific version of reality that we directly experience? Ethically, the multiverse raises challenging questions about our responsibilities toward parallel selves and universes. If our actions spawn new branches of reality, do we bear moral responsibility for all versions of those actions across the multiverse? Are we accountable not just for what happens in our branch, but for all possible consequences of our choices? Some argue that multiverse ethics would emphasize the quality of character and intention over specific outcomes, since all possible outcomes occur somewhere. Others suggest it might lead to a form of ethical consequentialism that considers the distribution of outcomes across all branches, seeking actions that produce the greatest good in the most branches of reality. Religious and spiritual perspectives on the multiverse vary widely. Some see the potential infinity of universes as compatible with divine creation, with God creating not just one universe, but a vast multiverse encompassing all possibilities. Others view the multiverse as challenging traditional religious cosmologies centered on a single creation. The concept of communication between universes has parallels in various mystical traditions. Many spiritual practices describe experiences of accessing other planes of reality or dimensions of consciousness, which might represent intuitive perceptions of the multiverse structure. The scientific exploration of parallel universes might provide new frameworks for understanding these spiritual experiences. For instance, reports of past life memories, prophetic dreams, or synchronicities might be reinterpreted as fragments of information leaking between parallel branches of reality. What mystics have described as accessing the Akashic records might be understood as perceiving information from across the multiverse, glimpsing the roads not taken and the lives not lived in this particular branch. These philosophical reflections lead us to practical questions about how we might actually detect signs of parallel universes or communication between them. What evidence might we look for, and how might we distinguish genuine signals from the background noise of our own universe? The search for signs of parallel universes begins with cosmological observations. The cosmic microwave background radiation, the afterglow of the Big Bang that permeates our universe, might contain subtle patterns indicating interactions with other universes. Scientists have analyzed this radiation for anomalies or unexpected correlations that might suggest the influence of parallel realities. One specific signature might be circular patterns in the cosmic microwave background, potentially caused by collisions between our universe and neighboring bubble universes. These collision events would create distinctive temperature variations, circular regions with different properties than their surroundings. Several candidate patterns have been identified, though none have been confirmed as definitive evidence of parallel universes. Cold spots in the cosmic microwave background, regions with temperatures significantly below the average, present another potential sign. In 2013, astronomers identified an unusually large cold spot that some theorists suggested might result from the gravitational influence of a parallel universe or represent a quantum entanglement effect across universe boundaries. Gravitational wave astronomy offers another observational window. The LIGO and Virgo detectors have recently begun detecting gravitational waves from black hole and neutron star mergers, opening a new era in observational astronomy. These detectors might eventually identify gravitational wave patterns that cannot be explained by events within our universe, potentially indicating influences from parallel realities. Some theories suggest that dark matter, the mysterious substance that appears to hold galaxies together, might actually be ordinary matter in parallel universes, gravitationally influencing our own. Detailed mapping of dark matter distribution might reveal patterns indicating the structure of neighboring universe brains gravitationally interacting with ours. Dark energy, the even more mysterious force accelerating our universe's expansion, might similarly represent an influence from beyond our universe. If our universe is one brain floating in a higher dimensional bulk, the acceleration might result from interactions with other brains or the bulk itself. Precise measurements of cosmic acceleration might reveal variations or patterns indicating such extra-universal influences. At the quantum scale, experiments testing quantum entanglement might reveal evidence of multiverse connections. If entangled particles are indeed connected through microscopic wormholes, as some theoretical frameworks suggest, these connections might extend beyond our universe to entangled particles in parallel branches of reality. Experiments with quantum computers might provide another avenue for detecting multiverse communications. If quantum computations indeed harness processing power from parallel universes, as David Deutsch has suggested, careful analysis of quantum algorithms might reveal patterns indicating information flow between universe branches. These patterns might manifest as statistical anomalies in quantum measurements that could only be explained by multiverse interactions. Neutrino detectors represent another experimental frontier. Neutrinos, nearly massless particles that rarely interact with ordinary matter, might occasionally originate from or be influenced by parallel universes. Anomalous neutrino detections or unexpected patterns in neutrino oscillations might indicate interactions across universe boundaries. Cosmic ray observations provide yet another window. Ultra-high energy cosmic rays, subatomic particles that strike Earth's atmosphere with energies millions of times greater than particles in our most powerful accelerators, might occasionally originate from parallel universes. If particles could traverse the barriers between universes under specific conditions, they might appear in our detectors with energy signatures or arrival patterns inconsistent with particles accelerated by known cosmic processes. The Large Hadron Collider and future particle accelerators might produce evidence for extra dimensions or parallel universes. Some theories suggest that microscopic black holes might be created in high-energy collisions, potentially providing channels for energy or information to leak into parallel realities. The energy signatures of such events would differ from standard particle collision results, potentially providing evidence for multiverse connections. Even more exotic detection methods have been proposed. Some scientists suggest looking for time-reverse signals, information that appears to travel backward in time, which might actually represent information leaking from parallel universe branches with different temporal orientation. Others propose searching for violations of conservation laws that might indicate energy or information entering our universe from parallel realities. Astronomical surveys might identify regions of space with unusual properties, potentially indicating boundaries or overlap zones between universe bubbles. These might manifest as unexpected variations in the constants of nature, regions where physical laws appear slightly different from the surrounding space. The search for technosignatures, evidence of advanced civilizations, might also reveal signs of multiverse communication. An extraordinarily advanced civilization might develop technologies to detect or even communicate with parallel universes. Such civilizations might leave distinctive signatures in astronomical data, artifacts of their multiverse communication technologies that we might detect. The Fermi paradox, the puzzle of why we haven't detected signs of extraterrestrial civilizations, despite the high probability of their existence, might be explained by a multiverse perspective. Perhaps advanced civilizations typically discover ways to migrate to or communicate with more hospitable parallel universes, explaining their apparent absence in our particular branch of reality. All these search methods face significant challenges. The signals from parallel universes would likely be extremely subtle, easily lost in the noise of natural processes within our own universe. Distinguishing genuine multiverse communications from statistical flukes or unknown natural phenomena would require extraordinary evidence and careful analysis. Moreover, we might not recognize communications from parallel universes, even if we detected them. If these universes operate under different physical laws or contain radically different forms of matter and energy, their signals might appear as inexplicable anomalies rather than recognizable patterns. We would be like early radio pioneers detecting signals without understanding the encoding, unable to extract meaningful information. Yet despite these challenges, the search continues. New astronomical instruments, more sensitive detectors, and more sophisticated data analysis techniques continue to expand our observational reach. Even without definitive proof, these searches enhance our understanding of the cosmos and establish increasingly stringent constraints on theoretical models. The absence of clear evidence does not disprove the multiverse hypothesis. Many scientific theories began with mathematical predictions long before experimental confirmation. The existence of black holes was predicted mathematically decades before astronomical observations confirmed them. Gravitational waves were predicted by Einstein in 1916, but not directly detected until 2016, a century later. This historical pattern reminds us that absence of evidence is not evidence of absence. The multiverse might be real and even in communication with our universe through channels we have not yet learned to detect. As we advance our experimental frontiers, we might find the first empirical evidence for parallel universes hiding in data we already possess but have not correctly interpreted. As we continue our search for signs of parallel universes, we must also explore the experimental frontiers that might allow us to test multiverse theories directly. What current and future experiments might provide evidence for or against the existence of parallel universes and communication between them? Cosmic microwave background missions represent one of the most promising experimental frontiers. Satellites like the European Space Agency's Planck Observatory have mapped the cosmic microwave background with unprecedented precision, providing data that cosmologists continue to analyze for signs of multiverse interactions. Future missions with even greater sensitivity might detect the subtle patterns indicating collisions with other universe bubbles or quantum entanglement across universe boundaries. Gravitational wave astronomy, only recently made possible by detectors like LIGO and Virgo, offers another experimental frontier. These observatories detect ripples in space-time caused by massive accelerating objects like colliding black holes. As the sensitivity of these detectors improves and new observatories come online, they might detect gravitational waves with unexpected properties, potentially indicating influences from beyond our universe. The next generation of gravitational wave detectors includes space-based observatories like LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s. By placing gravitational wave detectors in space, free from Earth's seismic noise, these observatories will be able to detect much subtler gravitational waves across a wider frequency range, potentially revealing signals from parallel universes. Quantum experiments represent another crucial frontier. Advances in quantum computing and quantum information science continue to push the boundaries of what we can observe and manipulate at the quantum level. Experiments testing quantum entanglement over increasingly large distances and timescales might reveal anomalies indicating connections across universe branches. Quantum simulation experiments are particularly relevant to multiverse research. These involve using controllable quantum systems to simulate the behavior of other quantum systems that are difficult to study directly. Some quantum simulations might effectively create miniature parallel universes within our own, providing insights into how communication between universes might work. A quantum experiment called the double slit with a quantum eraser demonstrates how quantum information can influence particles through what appears to be backward causation, with future measurements affecting past behavior. Some physicists suggest this might represent information flow between universe branches, providing a model for how multiverse communication might manifest experimentally. Neutrino observatories continue to expand our understanding of these elusive particles. Facilities like IceCube at the South Pole, which uses a cubic kilometer of Antarctic ice to detect neutrino interactions, might identify neutrinos with unexpected properties or behaviors indicating multiverse origins. Future observatories with even greater sensitivity might detect the subtle signals of neutrinos that have interacted with or originated from parallel realities. Particle accelerators push the frontiers of high-energy physics. the Large Hadron Collider at CERN, which confirmed the existence of the Higgs boson in 2012, continues to search for exotic particles and phenomena that might indicate extra dimensions or parallel universes. Future accelerators with even higher energies might create conditions where the barriers between universes temporarily thin, allowing for detectable interactions. One specific prediction of some multiverse theories is the existence of mini black holes that might be produced in high-energy particle collisions. These microscopic black holes would evaporate almost instantaneously through Hawking radiation, but the specific pattern of this radiation might indicate whether the black hole connected to parallel universes before evaporating. Astronomical observatories across the electromagnetic spectrum continue to map our universe with increasing precision. The James Webb Space Telescope, launched as a successor to the Hubble Space Telescope, provides unprecedented views of distant galaxies and the early universe. Unexpected patterns in the distribution of galaxies or in the cosmic web of dark matter might indicate gravitational influences from neighboring universe brains. Dark matter detection experiments represent another experimental frontier. Various technologies attempt to directly detect the particles that might constitute dark matter, from deep underground detectors looking for rare collisions with ordinary matter to space-based telescopes, mapping the distribution of dark matter through its gravitational effects. If dark matter partly consists of influences from parallel universes, these experiments might reveal its exotic properties. Advanced computer simulations allow scientists to model the evolution of the universe and test different multiverse theories against observational data. As computing power increases, these simulations become more sophisticated, potentially revealing subtle signatures of multiverse physics that we should look for in astronomical data. Quantum gravity experiments attempt to probe the regime where quantum mechanics and general relativity intersect, the domain where multiverse physics would operate. While a complete theory of quantum gravity remains elusive, experiments testing aspects of proposed theories might provide evidence for or against different multiverse models. For instance, holographic noise experiments search for quantum fluctuations in space itself, testing the holographic principle that suggests our three-dimensional reality emerges from information encoded on a two-dimensional boundary. Evidence supporting the holographic principle would lend credence to multiverse models based on this principle. Analog gravity experiments use physical systems like Bose-Einstein, condensates, or flowing fluids to simulate aspects of gravitational physics, including the behavior of black holes and wormholes. These experiments might provide insights into how information travels in exotic space-time configurations, potentially including passages between universes. Experiments with entangled quantum particles continue to test the foundations of quantum mechanics. Bell test experiments, which have conclusively demonstrated the non-local nature of quantum entanglement, might be extended to search for correlations that could only be explained by connections between universe branches. The technological challenges facing these experiments are significant. Detecting signals from parallel universes would require extraordinary sensitivity and precision, distinguishing subtle anomalies from instrumental noise and known physical processes. The energy scales at which multiverse physics becomes apparent might lie far beyond what our current technology can access. Moreover, these experiments face conceptual challenges. How do we design experiments to test theories that inherently involve realms beyond our direct observation? How do we distinguish evidence for parallel universes from alternative explanations involving unknown physics within our universe? These questions require careful experimental design and rigorous analysis of results. Despite these challenges, experimental physics continues to advance, pushing the boundaries of what we can observe and test. Each new observatory, detector, or experiment extends our reach, bringing us closer to potential evidence for or against the existence of parallel universes and communication between them. These experimental frontiers represent not just technical achievements, but philosophical ones as well. They embody humanity's deep curiosity about the fundamental nature of reality and our determination to test even the most seemingly outlandish theories against empirical evidence. The search for parallel universes and potential communication between them exemplifies science at its most ambitious, reaching beyond the immediately observable to explore the deepest structures of reality. The story of multiverse research also highlights the interplay between theory and experiment. Mathematical models suggest possibilities that experiments then test, with experimental results refining the theories in an ongoing dialogue. This process has characterized scientific progress for centuries, leading to ever deeper understanding of the cosmos and our place within it. As these experiments continue, they promise to either find evidence supporting multiverse theories or constrain these theories with increasingly precise limits. Either outcome advances our knowledge, bringing us closer to understanding whether we inhabit a singular universe or one reality among many, whether we exist in isolation or as part of a vast cosmic conversation spanning parallel worlds. Our tools grow ever sharper, from space-based observatories mapping the cosmos to quantum technologies manipulating individual particles. Yet the universe remains elusive, revealing its secrets slowly and often in unexpected ways. The search for parallel universes and communication between them may lead to discoveries we cannot currently imagine, opening new frontiers in our understanding of reality itself. Whether multiverse theories ultimately prove correct or not, the journey of exploring them has already enriched our understanding of quantum mechanics, cosmology, and the foundations of physics. The questions raised by these theories have spurred new mathematical frameworks, experimental techniques, and philosophical perspectives, demonstrating how the pursuit of even seemingly speculative ideas can advance the frontiers of knowledge. As we continue this exploration, we must maintain both scientific rigor and imaginative openness. The history of science teaches us that reality often exceeds our preconceptions, revealing structures and phenomena more extraordinary than we initially imagined. Parallel universes in communication with our own may seem fantastical, but so too did many concepts now established in mainstream physics, from quantum entanglement to black holes to the expansion of the universe itself. The quest to understand parallel universes and potential communication between them represents science at its most profound, probing the very nature of reality and our place within it. This journey combines mathematical elegance, experimental ingenuity, and philosophical depth, challenging us to expand our conception of what exists beyond the immediately observable. Through this exploration, we may ultimately discover that our universe is not a solitary island, but part of a vast archipelago of realities, connected through subtle channels of communication. Or we may find that our universe truly stands alone, unique and singular in its existence. Either discovery would profoundly transform our understanding of reality and our place within the cosmic order. As we await the results of current and future experiments, we continue to refine our theories and sharpen our questions. The mathematics suggesting parallel universes grows increasingly sophisticated, providing more precise predictions that experiments can test. The technologies enabling these experiments continue to advance, extending our observational reach into ever more exotic realms of physics. This ongoing dialogue between theory and experiment, between mathematical possibility and empirical reality, embodies the scientific quest to understand the cosmos in all its complexity. Through this process, we edge closer to answering one of humanity's most profound questions. Is our universe all that exists, or are we part of a greater multiverse, perhaps engaged in an ongoing conversation across the boundaries between worlds? The answer to this question awaits discovery on the experimental frontiers of physics, in the subtle patterns of cosmic radiation, the behavior of quantum particles, and the ripples of gravitational waves. As we continue to explore these frontiers, we participate in humanity's greatest intellectual adventure, the quest to understand the true nature of reality in all its vast and possibly multiple expressions. As we approach the conclusion of our journey through the mysteries of parallel universes, we must consider perhaps the most provocative question of all. If parallel universes do communicate, what then? How might the confirmation of multiverse communication transform our understanding of reality itself? And what implications would this have for physics, philosophy, and our very conception of existence? The confirmation that information flows between parallel universes would represent one of the most profound scientific discoveries in human history. It would fundamentally transform physics, requiring the revision of theories that assume our universe exists in isolation. The boundaries between quantum mechanics and cosmology would blur, creating a new unified framework for understanding reality as an interconnected multiverse rather than a singular universe. The laws of conservation that form the foundation of modern physics might need reconsideration. If energy or information can transfer between universes, then conservation laws might apply not to our universe alone, but to the multiverse as a whole. What appears as a violation of conservation in our universe might simply represent a transfer to or from parallel realities, preserving conservation across the greater multiverse. The arrow of time itself might be reconceptualized. If parallel universes with different temporal orientations communicate, then the unidirectional flow of time that characterizes our experience might be just one manifestation of a more complex multiversal temporality. Information flowing between universes might appear to violate causality from our perspective, while maintaining consistency within the broader multiverse framework. The concept of physical law would expand beyond our universe to encompass the structure of the multiverse itself. Scientists would seek meta-laws that govern how different universe branches form and interact, principles that transcend the physics of any single universe to describe the architecture of reality at its deepest level. Cosmology would undergo a revolution comparable to the Copernican shift that moved Earth from the center of the cosmos. Just as we came to understand our planet as one world orbiting one star in one galaxy, we would recognize our universe as one reality among countless others, all potentially in communication through cosmic channels. This cosmological revolution would likely spark technological revolutions as well. The confirmation of communication between universes would inspire efforts to enhance and control these channels, developing technologies to send and receive information across the multiverse. Quantum computers might be reconceptualized as multiverse communication devices, their power coming from distributed computation across parallel realities. While traveling physically between universes would likely remain beyond our capabilities due to the enormous energy requirements, information exchange might become increasingly sophisticated. Scientists might develop techniques to encode and decode messages passing through quantum channels, gradually establishing more reliable communication with parallel branches of reality. The practical applications of such technologies would be difficult to predict, but potentially transformative. Access to information from parallel universes might provide unprecedented computational resources, effectively allowing us to outsource calculations to the multiverse. Problems currently considered computationally intractable might become solvable through distributed processing across reality branches. Even more intriguing is the possibility of accessing knowledge from parallel universes, where historical developments took different paths. We might learn of scientific discoveries or technological innovations that occurred in other branches, but not in our own, accelerating our development by incorporating insights from alternate historical trajectories. Such knowledge transfer would raise profound questions about intellectual property and attribution. How do we credit discoveries originating in parallel universes? Would this represent a form of cosmic collaboration, with knowledge flowing between different versions of humanity across the multiverse? The confirmation of multiverse communication would also transform our understanding of consciousness and its relationship to physical reality. If quantum processes in the brain do indeed sample information from across multiple universe branches, as some theories suggest, then consciousness itself might be reconceptualized as inherently multiversal, an awareness that spans reality branches rather than being confined to one. This perspective aligns with reports from altered states of consciousness, where individuals describe accessing information beyond their normal awareness. Experiences currently categorized as mystical or transcendent might be reinterpreted as momentary expansions of consciousness across universe branches, brief glimpses of the multiversal nature of mind itself. Neural networks and artificial intelligence might provide models for understanding this distributed consciousness. Just as neural networks process information across distributed nodes, consciousness might process information across distributed reality branches, integrating inputs from parallel versions of ourselves to generate our unified sense of experience. The very concept of self would evolve in response to the confirmation of multiverse communication. Rather than identifying solely with one version of ourselves in one universe branch, we might develop a more expanded identity that acknowledges our parallel selves across the multiverse. This expansion of identity might foster both humility and wonder, recognizing ourselves as both smaller than we imagined, just one version among many, and simultaneously part of something far greater, a multiversal entity spanning countless realities. This shift in perspective might transform how we view our choices and their consequences. Knowing that all possibilities are realized somewhere in the multiverse might liberate us from regret about roads not taken, while simultaneously deepening our commitment to creating positive outcomes in this particular branch of reality that we directly experience. Ethically, this perspective might foster greater responsibility rather than diminishing it. Recognizing that our actions spawn new universe branches might inspire more careful consideration of the consequences of our choices across the multiverse. We might strive to make decisions that create positive outcomes in the greatest number of resulting branches, maximizing well-being across the multiversal tree of possibilities. Environmentally, the multiverse perspective offers both caution and hope. It reminds us that there may be universe branches where humanity failed to address climate change or other existential threats, resulting in disaster. Yet it also suggests branches where we succeeded, developing sustainable technologies and harmonious relationships with our planet. Our challenge becomes charting a course in this branch that aligns with the successful trajectories rather than the failed ones. Theological and spiritual traditions would engage with the multiverse concept in diverse ways. Some might see the multiverse as expanding rather than diminishing the divine, with God encompassing all possible realities rather than just one. Others might find in multiverse communication a scientific framework for concepts previously expressed in mystical terms, from non-local consciousness to the interconnectedness of all being. The possibility that universe branches might represent different expressions of an underlying cosmic order could bridge scientific and spiritual perspectives. The multiverse might be neither purely random nor rigidly deterministic, but an exploration of all potential expressions of deeper principles, a cosmic creative process playing out across reality branches. Socially and culturally, confirmation of multiverse communication would likely influence art, literature, and popular imagination in profound ways. The multiverse concept already appears in fiction and film, but confirmation would transform it from speculative fantasy to scientific reality, inspiring new forms of expression that engage with this expanded conception of existence. Music might explore compositions that change based on probabilistic processes, mirroring the branching of universe pathways. Visual art might develop techniques for representing multiversal perspectives, perhaps showing multiple overlapping realities simultaneously. Literature might experiment with narratives that branch and reconnect, following characters across multiple universe trajectories. The psychology of hope and possibility might be transformed by the multiverse perspective. The knowledge that somewhere in the multiverse, things worked out differently, that challenges were overcome and disasters averted, might provide comfort and inspiration in the face of difficulties in our particular branch. This would not represent escapism, but a recognition of the genuine breadth of possibility inherent within multiversal reality. Education would evolve to incorporate multiverse concepts, teaching students not just about the history that did occur in our branch, but about the branching nature of possibility itself. A multiversal perspective on history would emphasize contingency and choice, helping students understand how small decisions can lead to vastly different outcomes over time. The humanities and sciences would find new points of convergence in multiverse studies. The philosophical implications of multiple realities would engage not just physicists, but philosophers, theologians, artists, and scholars across disciplines. This intellectual cross-pollination might generate new frameworks for understanding both the objective structure of the multiverse and its subjective meaning for conscious beings within it. Perhaps most profoundly, the confirmation of multiverse communication would transform our basic conception of reality itself. Reality would no longer be singular and fixed, but plural and interwoven, a tapestry of interconnected branches rather than a linear progression. This shift in perspective might represent the most significant expansion of human understanding, since we recognized Earth as one planet circling one star in a vast cosmos. The fluidity of reality, implied by multiverse communication, challenges our conventional distinctions between actual and potential, real and imaginary. If all possibilities manifest somewhere in the multiverse, and information flows between these manifestations, then the boundaries between what is and what might be become permeable. Reality becomes not a single actualized state, but a superposition of possibilities in constant dialogue. This conceptual shift would reflect developments already occurring in quantum physics, where the rigid determinism of classical mechanics has given way to probability waves and superposition states. The multiverse perspective extends this quantum uncertainty from the microscopic to the cosmic scale, suggesting that the entire universe exists in multiple overlapping configurations connected through quantum channels. The mathematical formalism supporting this view emerges from quantum mechanics itself. The Schrödinger equation, which describes how quantum systems evolve over time, does not inherently include wave function collapse, but rather depicts reality as branching into superpositions of all possible outcomes. The multiverse interpretation takes this mathematics at face value, suggesting that reality does indeed branch with each quantum event, creating parallel universes that may remain in communication through quantum entanglement. If these parallel branches do communicate, then reality might be more malleable than we previously understood. The boundaries between different branches might be permeable under certain conditions, allowing for information leakage between worlds that we typically experience as separate. This permeability might manifest in subtle quantum effects that we are only beginning to detect and understand. The fluid conception of reality suggested by multiverse communication aligns with ancient philosophical traditions that emphasize impermanence and interconnection. From Buddhism's concept of dependent origination to Heraclitus's observation that one cannot step into the same river twice, wisdom traditions across cultures have suggested that reality is not fixed, but constantly changing and interwoven. The multiverse perspective might provide a scientific framework for these philosophical insights, uniting contemporary physics with ancient wisdom. This view of reality as fluid and interconnected carries practical implications for how we navigate our lives. Rather than seeing our path as rigidly determined or completely random, we might recognize ourselves as moving through a probability landscape, making choices that shape which branch of reality we experience while remaining connected to other possibilities through quantum channels. The recognition that reality might be influenced by flows of information from parallel universes invites a more participatory relationship with existence itself. Rather than seeing ourselves as passive observers of a predetermined world, we might recognize our role in helping shape which probability branches manifest in our experience, collaborating with reality rather than merely witnessing it. This participatory understanding of reality echoes quantum measurement theory, where the act of observation influences what is observed. If parallel universes communicate, then the boundary between observer and observed blurs further, with consciousness potentially receiving and integrating information from across multiple branches of reality. As remarkable as these possibilities may seem, we must maintain scientific humility in our explorations. The confirmation of multiverse communication, if it occurs, will likely reveal a reality even stranger and more wonderful than our theories currently suggest. Throughout history, major scientific revolutions have not merely confirmed existing speculations, but revealed unexpected dimensions of reality that transformed our understanding in unanticipated ways. Whether parallel universes communicate or not, the questions raised by these investigations continue to deepen our understanding of quantum mechanics, cosmology, and the foundations of physical reality. The journey of exploration itself enriches our knowledge and expands our perspective, regardless of its ultimate destination. As we contemplate these profound possibilities, we must acknowledge that the mystery of parallel universes remains largely unresolved. Despite decades of theoretical work and increasingly sophisticated experiments, definitive evidence for parallel universes, let alone communication between them, continues to elude us. This chapter explores what we currently know, what remains unknown, and the wonder that persists in the face of cosmic mystery. Our mathematical models strongly suggest the possibility of a multiverse. From the many worlds interpretation of quantum mechanics, to the eternal inflation model in cosmology, to the landscape of string theory, multiple theoretical frameworks independently point toward the existence of parallel realities. The convergence of these different approaches lends credibility to the multiverse hypothesis, even in the absence of direct observational evidence. Yet mathematics is not reality itself, but a language we use to describe reality. The fact that our equations suggest parallel universes does not guarantee their existence. Throughout scientific history, mathematically elegant theories have sometimes failed to match experimental evidence, requiring revision or replacement. The multiverse might similarly represent a mathematical possibility that nature does not actualize. The observational evidence for parallel universes remains tantalizing but inconclusive. Anomalies in the cosmic microwave background, unexpected patterns in gravitational wave data, and curious results in quantum experiments might hint at influences from beyond our universe, but alternative explanations within conventional physics cannot be ruled out. This evidentiary gap does not invalidate multiverse theories, but places them in the category of plausible hypotheses awaiting confirmation. They represent not proven fact, but fruitful avenues for investigation, directions of inquiry that might eventually lead to revolutionary discoveries, or might require significant revision as new evidence emerges. The question of communication between universes faces even greater empirical challenges. Even if parallel universes exist, they might be entirely separate, with no information flow between them. The apparent randomness of quantum events might not represent signals from parallel branches, but genuine indeterminacy at the foundation of reality. Our understanding of quantum decoherence suggests that macroscopic objects rapidly lose quantum coherence through environmental interactions, potentially severing any communication channels between universe branches before they can carry meaningful information. This process might explain why we don't experience obvious signs of multiverse communication in everyday life, even if the underlying reality is fundamentally multiversal. The theoretical models suggesting multiverse communication remain works in progress, with significant unresolved questions about mechanisms, bandwidth, and detectability. The mathematical formalism connecting quantum entanglement to wormholes, for instance, requires further development and experimental testing before it can be considered established science. These uncertainties reflect not failure, but the frontier nature of multiverse research. We stand at the edge of known physics, peering into realms where our theories remain incomplete and our experimental capabilities limited. This position invites both scientific caution and imaginative exploration, a balanced approach that acknowledges limitations while remaining open to revolutionary possibilities. The history of science reminds us that major theoretical advances often precede experimental confirmation by decades or even centuries. Democritus proposed atomic theory in ancient Greece, but direct evidence for atoms awaited 19th and 20th century experiments. Continental drift was proposed in 1912, but not widely accepted until the 1960s, when plate tectonics provided a mechanism and supporting evidence. This historical pattern suggests that the current gap between multiverse theory and observational evidence does not necessarily indicate a flaw in the theory. Rather, it might reflect the inevitable delay between conceptual breakthroughs and the development of technologies capable of testing them. Future instruments and experimental techniques might provide the evidence that currently eludes us. Moreover, the absence of conclusive evidence does not diminish the intellectual value of multiverse theory. Even as a working hypothesis, the multiverse concept has generated productive research programs, inspired new mathematical approaches, and deepened our understanding of quantum mechanics and cosmology. Scientific progress often emerges from exploring possibilities that challenge conventional wisdom, regardless of whether those possibilities are ultimately confirmed. The mystery surrounding parallel universes and potential communication between them also holds value beyond strictly scientific considerations. It reminds us of the vastness of what remains unknown, fostering intellectual humility in the face of cosmic complexity. This humility does not represent anti-intellectualism, but its opposite, a sophisticated recognition that reality may extend far beyond our current understanding. The unknown aspects of multiverse physics invite continued exploration and wonder. They challenge us to develop more sophisticated theories, more sensitive instruments, and more creative experimental approaches. The questions left unanswered are not failures, but opportunities, invitations to push beyond the boundaries of established knowledge. This perspective aligns with the history of science as an ongoing journey rather than a collection of settled conclusions. From Newtonian mechanics to general relativity, from classical physics to quantum mechanics, scientific understanding has repeatedly transformed through revolutionary insights that revealed previous theories as special cases within broader frameworks. The multiverse concept may represent another step in this ongoing expansion of scientific perspective. As we acknowledge the mysteries that remain, we also celebrate the remarkable progress already achieved. A century ago, the concept of parallel universes would have seemed purely speculative, disconnected from mainstream physics. Today, it emerges naturally from our most successful physical theories, a possibility taken seriously by leading scientists worldwide. This transformation reflects not a lowering of scientific standards, but the opposite, the rigorous pursuit of mathematical models that fully account for quantum phenomena and cosmological observations. The multiverse concept has moved from science fiction to scientific hypothesis through this process of rigorous theoretical development, even as definitive observational evidence remains elusive. The continuing mystery surrounding parallel universes also serves as a reminder that nature is not obligated to conform to our intuitions or preferences. Throughout scientific history, reality has repeatedly proven stranger than common sense would suggest, from the curvature of space-time to the uncertainty principle to quantum entanglement. Parallel universes in communication with our own may seem fantastical, but no more so than many established features of quantum mechanics once did. This historical perspective invites us to hold our theories lightly while pursuing them rigorously, maintaining both skepticism and openness as we explore the frontiers of physics. The mystery is not something to be eliminated, but to be engaged with, a creative tension that drives scientific progress through the interplay of theory, experiment, and wonder. Perhaps most importantly, the mystery of parallel universes connects us to the fundamental human experience of facing the unknown. From our earliest ancestors gazing at the stars to contemporary physicists developing multiverse theories, humans have always contemplated possibilities beyond immediate experience, reaching toward understanding while acknowledging the vastness of what remains mysterious. This balance between knowledge and mystery, between what we have learned and what remains to be discovered, characterizes science at its best. The ongoing exploration of parallel universes exemplifies this balance, combining sophisticated mathematics, an experimental ingenuity with an openness to possibilities that stretch our conception of reality itself. Whether parallel universes exist and communicate or not, the journey of investigating these possibilities enriches our understanding and expands our perspective. It reminds us that reality may be far vaster and more wonderful than our everyday experience suggests. A cosmic landscape of possibility extending far beyond the horizons of our current knowledge. As we continue this exploration, we remain both scientists and dreamers, analyzing data while imagining possibilities, calculating probabilities while contemplating wonders. This dual approach has characterized human inquiry throughout history, driving us to discover what is while remaining open to what might be. The mystery remains, not as an obstacle to understanding, but as an invitation to deeper exploration. It challenges us to develop more sophisticated theories, more sensitive instruments, and more creative experimental approaches. It reminds us that science is not a completed edifice, but an ongoing journey of discovery, with new horizons continually emerging as our understanding expands. In this spirit of ongoing exploration and wonder, we conclude our journey through the mysteries of parallel universes and potential communication between them. Not with definitive answers, but with deepened questions, not with certainty, but with expanded possibility, not with closure, but with continued openness to the extraordinary vastness and complexity of cosmic reality. As our exploration of parallel universes and the possibility of communication between them draws to a close, we find ourselves returning to the fundamental wonder that initiated our journey. We began with a question that stretches the boundaries of imagination. Do parallel universes exist? And if so, could they somehow communicate with each other? We end not with a definitive answer, but with a deeper appreciation for the question itself and all it reveals about the nature of reality and our place within it. Throughout our journey, we have traversed the landscape of contemporary physics, from the many worlds interpretation of quantum mechanics to the brain worlds of string theory, from the mysteries of wormholes to the mathematics of the holographic principle. We have explored how these frameworks might allow for communication between separate realities, creating cosmic conversations across the multiverse. We have considered what signs of such communication we might detect, from patterns in the cosmic microwave background to anomalies in gravitational waves, from quantum correlations to cosmic coincidences. We have examined the experimental frontiers where evidence might emerge, from quantum computers to particle accelerators, from cosmological observations to quantum entanglement tests. We have reflected on the philosophical implications of a communicating multiverse, from questions of identity and free will to the nature of consciousness and reality itself. We have contemplated how the confirmation of parallel universes in communication might transform our understanding not just of physics, but of existence itself. Throughout this exploration, we have maintained both scientific rigor and imaginative openness, acknowledging the gap between theoretical possibility and experimental confirmation, while recognizing that this gap has characterized many scientific advances throughout history. The absence of definitive evidence does not invalidate the quest, but places it at the frontier of human knowledge, where the known meets the unknown in creative tension. As we conclude, we might imagine the vast multiverse as an infinite ocean of possibility, with our universe as one wave among countless others. These waves might appear separate on the surface, but remain connected at deeper levels, their waters mingling in subtle currents far below what we can easily observe. The communication between universes might resemble these hidden currents, flows of information passing between apparently separate realities through quantum channels or dimensional connections. Perhaps parallel universes do speak, but in whispers beyond our current ability to hear clearly. Their messages might be encoded in the quantum foam at the foundation of space-time, in the subtle correlations between particles, in the faint patterns of cosmic radiation that permeate our universe. These whispers might carry echoes of roads not taken, of possibilities unrealized in our branch, but actualized in others, of cosmic siblings separated at birth, but still faintly connected. If such communication exists, it would transform our understanding of isolation and connection. Our universe would not be a solitary island, but part of a vast archipelago of realities, separate on the surface, but connected through hidden channels. This connectedness would not diminish the uniqueness of our particular reality, but would place it within a greater context, a single instrument within a cosmic orchestra playing the symphony of existence. This perspective invites both humility and wonder. Humility in recognizing that our universe, vast as it appears, might be just one expression of a far greater reality. Wonder in contemplating the extraordinary richness this implies, the infinite tapestry of possibility woven across the multiverse. Both responses enrich our relationship with existence, fostering both scientific curiosity and philosophical depth. As we gaze at the night sky, we typically perceive distant stars and galaxies as the extent of what exists. The multiverse perspective suggests something more extraordinary, that beyond the visible cosmos lie other universes, other realities unfolding in parallel to our own. The darkness between stars might not be empty, but filled with alternate worlds, invisible to our telescopes, but suggested by our mathematics, and perhaps occasionally whispering to us through quantum channels. This expanded cosmic perspective echoes ancient wisdom traditions that have long suggested reality extends beyond immediate perception, from Plato's allegory of the cave to Buddhist concepts of interpenetrating realms. Human insight has repeatedly pointed toward layers of existence beyond the immediately apparent. The scientific exploration of parallel universes represents a contemporary approach to this perennial intuition, using mathematics and experiment to probe what was once accessible only through philosophy or mystical experience. The multiverse concept also aligns with the creative human impulse to imagine alternatives, to envision worlds that differ from our own. From literature to art to dreams, humans have always created parallel realities in imagination. The scientific multiverse theory suggests that this creative impulse might reflect a fundamental feature of reality itself, a cosmic creativity that actualizes all possibilities across parallel branches of existence. Whether parallel universes remain a beautiful mathematical possibility or eventually gain experimental confirmation, the journey of exploration has already enriched our understanding. It has pushed the boundaries of physics, generated new mathematical approaches, inspired philosophical reflection, and expanded our conception of what might be possible within the structure of reality. This journey continues, with new theories being developed, new experiments being designed, and new perspectives emerging at the intersection of quantum mechanics and cosmology. Future generations will carry forward this exploration, perhaps developing technologies we cannot currently imagine, and discovering evidence that eludes our present capabilities. The conversation about parallel universes and communication between them represents not a concluded investigation, but an ongoing dialogue at the frontier of human understanding. As individual conscious beings within this vast cosmic context, we occupy a unique position. We are both tiny fragments of the cosmos, our lives unfolding on a small planet circling an ordinary star, and simultaneously remarkable entities capable of contemplating the multiverse itself. Our consciousness, whatever its ultimate nature, allows us to explore realities beyond immediate experience, to develop mathematics describing worlds we cannot directly observe, to imagine possibilities beyond the actualized present. This capacity for transcending immediate perspective places us in a special relationship with the cosmos. We are not merely passive observers, but active explorers, using observation, mathematics, and imagination to reach beyond the horizons of the directly perceived. Through this exploration, we participate in the universe becoming conscious of itself, the cosmos contemplating its own extraordinary multiplicity through the vehicle of human awareness. If parallel universes do communicate, perhaps consciousness plays a role in this cosmic conversation. Some interpretations of quantum mechanics suggest consciousness might be involved in the selection of which potential reality becomes actual experience. If so, then consciousness itself might represent a channel between universe branches, an awareness that samples and integrates information from across the multiverse. This perspective would place sentient beings at a unique nexus in the cosmic web, points where the multiverse becomes aware of itself. Through consciousness, the separate branches of reality might achieve a kind of integration, not physically merging, but becoming connected through awareness that spans their divisions. Whether this speculative possibility has any basis in physics remains to be determined, but it highlights the profound connection between cosmic questions about parallel universes and personal questions about the nature of consciousness and experience. The external exploration of the multiverse connects to the internal exploration of awareness itself, creating a dialogue between objective science and subjective experience. As our journey concludes, we return to the wonder that initiated it. The possibility of parallel universes in communication represents one of the most extraordinary frontiers in contemporary science, challenging us to expand our conception of reality while remaining grounded in mathematical rigor and experimental evidence. It invites us to look at the night sky with new eyes, to see beyond the visible stars to the possible universes that might exist alongside our own. In that vast cosmic perspective, our individual lives gain both humility and significance. Humility in recognizing ourselves as tiny fragments of an inconceivably vast multiverse. Significance in recognizing ourselves as conscious entities capable of contemplating that vastness, of developing mathematics to describe it, of designing experiments to probe its mysteries. Perhaps parallel universes do speak in whispers beyond our senses, and perhaps in that silence lies the beauty of the cosmos, forever unfolding, forever mysterious. Whether we eventually detect those whispers, or the multiverse remains a mathematical possibility beyond experimental confirmation, the journey of exploration itself enriches our understanding and expands our perspective on the extraordinary reality we inhabit. As you rest with these possibilities, allow your imagination to gently contemplate the vastness they suggest. Beyond the stars visible in the night sky might lie other universes, other realities unfolding in parallel to our own. The mathematics of physics hints at this extraordinary possibility, not as mere fantasy, but as a serious scientific hypothesis emerging from our most successful theories. Whether these parallel universes exist and communicate remains an open question that future generations will continue to explore. But the very possibility reminds us of the extraordinary nature of existence itself, the remarkable fact that reality might extend far beyond our immediate perception, an endless ocean of possibility of which our universe is but one wave. With this perspective, may you find both peace and wonder. Peace in connecting to something vastly greater than individual concerns. Wonder in contemplating the extraordinary cosmos that includes both visible stars and, perhaps, invisible universes beyond them. In that wonder lies the heart of both science and spirituality, the awe we feel when touching, even briefly, the magnificent mystery of existence itself.